Ever wondered why your home network, often uses addresses like 192.168 on something?
Mm-hmm.
Or maybe how huge companies manage these massive internal networks.
Mm-hmm.
All those computers, printers, thermostats even. How do they do it without needing a unique web address for every single thing?
Right, a publicly reachable address, you mean? Yeah.
Okay, so let's unpack this a bit. We're diving into really a foundational piece of how the internet works today. It's a document called RFC 1918.
That's our source for this deep dive, yeah. It's officially a best current practice published way back in February 96.
February 1996. And it talks about allocating addresses for, and this is their term, private internets.
Private internets, exactly.
They didn't just appear out of thin air, right? There's a reason for it.
Oh, definitely. The internet was growing incredibly fast back then. Way faster than anyone really expected.
And that created problems. Big ones.
Two main ones, really. First, there was a real fear we'd just run out of global IP addresses. The original IPv4 pool wasn't infinite.
Okay, scarcity. Makes sense. What was the other one?
And maybe even more pressing, honestly, was the complexity. Imagine if every single device on the planet needed its own unique public address.
Wow.
And every internet router had to know the path to every single one of them, the routing tables. They'd be unimaginably huge, unmanageable.
Right. It would just collapse under its own weight. So, chaos.
Pretty much. So RFC in 1918 came along with a really elegant solution, actually.
Which was?
They realized, look, not every device needs to talk directly to the entire global internet. Lots of devices just need to communicate locally.
Within their own network, like my laptop talking to my printer at home.
Exactly. Or servers within a company talking to each other. They don't need a global identity for that.
So the RFC kind of formalizes this idea. It creates categories.
Yeah, basically private hosts and public hosts.
Mm-hmm.
Private ones just need internal connectivity, maybe indirect access out. Public ones need that direct global reachability.
And it makes sense, right? For security, for management, you don't want every single internal device exposed directly to the whole internet.
Absolutely not. Think about internal databases, testing servers, security cameras, smart bulbs, all that stuff. It shouldn't be directly on the public net.
So how do they make this work technically? They needed addresses for these private networks.
Right. So the Internet Assigned Numbers Authority, IANA, they officially set aside specific blocks of IP addresses, reserved them.
Reserved them away from the public internet.
Correct. They said, these ranges, they're for internal use. Anyone can use them inside their private network without asking us.
And because they're only used inside private networks, the same address range can be used by millions of different homes and companies simultaneously.
Precisely. My 192.168.1.0 at home doesn't conflict with your 192.168.1.0 at your place. They're in separate private worlds.
Okay, so what are these ranges? I bet people recognize them.
Oh, for sure. There's the big one, option for large companies, 10.0.0.0 all the way through 10.25.255.255. That's millions and millions of addresses.
A 10 dot network.
Then there's a middle range, 172.16.0.0 through 172.31.255.255. You see that sometimes. And the most common one for home users and small businesses, 192.168.0.0 through 192.168.255.255.
That's the one, 192.168. You see it everywhere.
And the key is the routers that connect these private networks to the public internet, they're configured not to forward packets with these private source or destination addresses out onto the public internet.
Ah, so they contain the traffic. It stays local unless it's specifically translated, like through NAT.
Exactly. That containment is crucial. It prevents conflicts and keeps internal stuff internal.
Looking back, this seems, almost obvious, but the impact was huge, wasn't it?
Absolutely massive. First, it dramatically slowed down how quickly we were using up the public IPv4 addresses, bought us valuable time.
Okay, address conservation, big win.
Second, it gave network admins huge flexibility. They could design complex internal networks without needing permission or unique addresses for everything.
Made life much simpler.
And third, it helped clean things up. Some companies had sort of informally used address ranges internally before this. RFC 1918 gave them official safe ranges to use, avoiding accidental clashes with real public addresses.
Right, a designated space. Now, did the document see any downsides? Any potential problems?
It did acknowledge some complexity. Like, if you need to move a device from being purely internal to being publicly accessible, or if you merge two companies that both happen to use, say, the 10.x.x.x range internally.
Uh-oh, conflict.
Yeah, that often means renumbering a whole bunch of devices,
Yep.
changing their IP addresses, which can be a pain, even with tools like DHCP helping out. It's a known challenge.
So bring it back to the listener. What's the big takeaway? When you see 10 dot something, or 172.16, or 192.168,
It's not random. It's not an accident.
it's a direct result of this standard, RFC 1918 from 1996. A deliberate choice to make the internet scale to keep it manageable by creating these dedicated zones for private use.
Exactly. It was fundamental to allowing the internet to grow the way it has.
Right.
But it does make you think.
What's that?
Well, RFC 1918 solved a huge IPv4 problem, but we still often need devices to talk both privately and publicly, which usually involves network address translation, NAT, adding another layer.
True.
So the question is, looking forward, maybe with IPv6 or even newer ideas, how can network designs make it easier for devices to shift roles, to move more fluidly between needing just internal access and needing public access, without all the complexity of renumbering or heavy translation, especially now when so many devices move between networks all the time?
That's a really interesting thought, how to make that transition smoother in the future. Something to chew on.